Hey y'all, welcome back. So today we just kind of took a step back and reviewed all of the derivatives that you need to know and did a little practice with them. We also today in class practiced a bunch of multiple choice questions that I'll record on a separate video. But let's go through all the derivatives that you need to know and do one example problem, mostly involving the chain rule of each one. So first, the derivative of sine is cosine. And if we want to differentiate sine of x squared plus 5x, we would say g prime is equal to the derivative of sine, which is cosine, leave what's inside the parentheses alone, and then multiply by the derivative of the inside. So that would be 2x plus 5. The derivative of cosine is the opposite of sine. And so if we want to differentiate a cosine function, we'll have to make sure to make the derivative negative here. So we'll get negative 4 times the sine of 4x, and then using the chain rule, we'll multiply that by an extra 4. If you choose to simplify this, we'd have negative 4 times 4, which would be negative 16 sine of 4x. That's typically not going to be something that's required, but if it's a multiple choice question, it's going to be simplified like that. So just be ready to identify those as being the same. The derivative of tangent is secant squared. And so if we want to differentiate 2 times tangent of x cubed, m prime here will be 2 times secant squared of x cubed times 3x, let's close those parentheses, 3x squared. So that would be our derivative. And if we were to simplify it, we would multiply the 2 by the 3, and I could write this as 6x squared times secant squared x cubed. The derivative of secant is secant times tangent. Now, you want to be careful with secant and actually cosecant. We'll go over that in a minute. Make sure that, especially when you're dealing with the chain rule here, that what's inside the parentheses ends up in both the secant and the tangent on the derivative. And just like normally, how we would normally do chain rule, we do need to multiply by the derivative here, which would be 3. So if I were to simplify this, I'd write it as 15 times secant of 3x times tangent of 3x. The derivative of cosecant is similar to the derivative of secant. And that is the derivative of cosecant is the opposite of cosecant x times cotangent x. So the derivative of p of x over here, which is negative cosecant of 7x, is the opposite of cosecant 7x times cotangent of 7x. And then using the chain rule, we're going to multiply by 7. So I could pull all the constants, the coefficients all to the front. So negative 7 times cosecant of 7x times cotangent of 7x. The derivative of cotangent is the opposite of cosecant squared x. This is kind of similar to tangent. Look how those are set up. And the derivative of 3 times cotangent of sine x, we're going to have to use chain rule, just like on most of these. K prime x, or the derivative of k, is going to be negative cosecant squared of sine x times the derivative of sine x, which is cosine x. And there's not really much you can do to simplify this. Actually, there's really, I don't see anything that we would even want to do, so we're going to leave it like that. The derivative of e to the x is itself. Now, I want to be clear here. Let me actually skip down here to the derivative of a to the x. The derivative of a to the x is itself times the natural log of the base. And you might be wondering, well, why is e to the x different? Well, it actually isn't. The derivative of e to the x is going to be e to the x times the natural log of e. It's just so that it just so happens that the natural log of e is 1. And so you have e to the x times 1, which just simplifies to be e to the x. So the base of e is just kind of a special base here that we can kind of shortcut our way through here and just call it e to the x. So the derivative of 4 times e to the power of tangent x is we're going to have that 4, okay, times e, this is the same thing we started with here, e to the tangent x, but times the derivative of tangent x, which as we reviewed earlier, you can see it up here somewhere, I'm sure, secant squared x. So we're going to have times secant squared x. The derivative of the natural log is 1 over x. And just like how we talked about, I'm actually going to skip over before we do the example and take a look at log base a, which would be 1 over x times the natural log of a. Okay, you might be wondering again here, why is the natural log 1 different here? Well, it really isn't. We really do have this natural log. It's just that the base is e. And just like with our exponential derivative, we saw natural log of e is 1. So you typically don't write this. So it really is the same formula. It's just we're simplifying it just to make it a little easier to remember, I think. So h prime is going to be 2 times 1 over x squared plus 5x times the derivative of that expression, x squared plus 5x, which would be 2x plus 5. So you could clean this up a little bit and put the 2 and the 2x plus 5 in the numerator. 2 times 2x plus 5 is going to be 4x plus 10. So if we want to simplify this a little bit, here's what I'll do here is I'll move this up to give myself a little bit more room. That's pretty good. And we could rewrite this as 4x plus 10 over x squared plus 5x. And I don't think we really need to take it any further than that. All right, so if we have 8 to the power of secant x and we want to find the derivative, we're going to have 8 to the secant x times the natural log of 8. And that's how we would start it. That's how we would start any of these exponential derivatives. But then we need to use the chain rule and multiply by the derivative of secant. And we talked about secant earlier. We know it's secant times tangent. So I'm going to multiply by secant x times tangent x. There's not really anything we can do to simplify that, so I'm going to leave it alone. The derivative of log base 3 of sine x plus e to the x would be 1 over 3. Oh, not 3, sorry. 1 over sine x plus e to the x times the natural log of 3. This is sort of our baseline derivative, but then we need to multiply by the derivative of the inside. So that would be cosine x plus e to the x. Now, you've got to make sure to put parentheses around that, that inside derivative. But if you want to not worry about that, with all these logarithm derivatives where you end up with a 1 in the numerator, or maybe you have something more going on, but typically it's just a 1. It's usually easier to write this with this factor written in the numerator spot. So 1 times that is just going to be itself anyway. So I'm going to actually replace that 1 with the cosine x plus e to the x and erase all this. And it just looks a little cleaner. I think evaluating might be a little tad bit easier if we need to, like, say, evaluate this at x equals 0 or something along those lines. Yeah, so there you go. There's the derivative. Okay, now we're getting into the more advanced derivatives. These are going to be our inverse trig functions. So the inverse of sine, its derivative is 1 over the square root of 1 minus x squared. So if we want to differentiate arcsine of x cubed, it would be 1 over the square root of 1 minus x cubed squared times the derivative of x cubed, which is 3x squared. Now, just like with the last problem, anytime you have like a fraction with a 1 over and you're multiplying by an expression, it's going to be a little cleaner if we just multiply that numerator out. 1 times 3x squared is going to be 3x squared. And there you go. Really, the only thing that you could potentially do to simplify this is to square the x cubed. And so, yeah, this would be 3x squared over the square root of 1 minus x to the sixth. The derivative of arc cosine, or the inverse of cosine, is negative 1 over the square root of 1 minus x squared. So the derivative of w here would be negative 1 over the square root of 1 minus parentheses 2x plus 5 quantity squared. Now we do need to use the chain rule here. So we are going to have to multiply by the derivative of 2x plus 5, which is just 2. But just like we did in the last couple of problems, I'm going to not leave it there. I'm going to do the multiplication here. Negative 1 times 2 is negative 2. And I think I'll leave it like that. There's really no point in multiplying out this binomial. So I'm just going to leave it like that. The derivative of arctangent is 1 over 1 plus x squared. So the derivative of 3 times arctangent of 4x is going to be 3 times 1 over 1 plus 4x quantity squared times the derivative of 4x, which is 4. I do want to clean this up a little bit. 3 times 4 is 12. So 12 over 1 plus 4 squared is 16, and times x squared. Finally, we have the inverse derivative. So let's say that g is the inverse of f. So that's what that statement means. So if we want to find the derivative, that would be 1 over f prime of the derivative of f. So sometimes it's written like this, but if we're letting g be the inverse, then we're going to replace this f inverse with g. So now this is a question, okay, given that we have a point 3 comma 2 on f, okay, if that's the case, then we've got 2 comma 3 on g, just going to make a note of that, and the derivative of f at 3 is 7. In other words, the instantaneous rate of change of f at 3 is 7. Determine the derivative of the inverse of f, remember that's just g in this problem, at x equals 2. So what we're really looking for here is g prime at 2. So that'll be 1 over f prime of g of 2. It should be 1 over f prime. Now, g of 2 is 3. Okay, we established that right here. So f prime of 3 and f prime of 3 is given. It's 7. So our answer here is 1/7. So the instantaneous rate of change of the inverse of f of x at x equals 2 is 1/7. Okay, let's take a look at this section down here, which is talking about the limit definitions of the derivatives. Now, really the only one that we've really focused on is this first one, but sometimes the AP test will throw some alternate forms of this limit definition of the derivative at you. So I just want to make sure I explain and be very clear about how you would approach these problems. So this first one is just your straightforward. This is the one we've been using. This is the derivative of f of x. And if we want to, if we look at this example problem, basically the way that you find these limits is to recognize that it is just the definition of a derivative and treat it as a derivative problem rather than a limit problem. Because what this will equal is the derivative of tangent 2x. So it's always whatever function you see right here. You can ignore the minus. That's what we're going to differentiate. So if we want to differentiate tangent of 2x, that would be secant squared of 2x times 2. Or if you want to bring that 2 up to the front, 2 times secant squared 2x. I should box some of these, right? Maybe I'll go back and do that later. So the next one is very similar, okay, but the big difference here is instead of x, we have a value here, a. So this is going to be the derivative of that function. You're going to treat it very similar But we're going to evaluate it at x equals a. So you find the derivative first, then plug in that value. So let's first find the derivative of cosine of x. So that's like our f of x. Our f of x is cosine x. So our derivative there is negative sine x. So what we're really trying to find is the value of the derivative at pi over 2, which would be negative sine of pi over 2. Sine of pi over 2 is 1, so this thing equals negative 1. Now, this third one is really just a variation on the one we just saw. Okay, we're still going to find the derivative of f of x at x equals a. But just take a look at that equation. Just notice how it's written just slightly differently. And kind of the big difference here is we don't have an h approaches 0 here like we did on the rest of them. But really, this is the same thing. We just don't have that h in there. We're still going to approach it the same way. In this case, my function here is natural log x. Okay, that's my original function that I'm trying to differentiate. Okay, the derivative of natural log is just going to be 1 over x. Oh, hold up. Nope. Back it up. Okay. Big difference here. F of x is actually right here. Okay, we're actually differentiating natural log of not x, but x plus 3. A little tricky there. So the derivative here is going to be 1 over x plus 3 times the derivative of x plus 3, which is just 1, so I don't need to really worry about that. So if I want to find f prime at 5, okay, so that would be 1 over 5 plus 3. It's going to be 1 over, not 3. Gosh, I'm going crazy here. I'm sorry, y'all. A here's 2. What am I doing? Yeah, you can definitely be tempted to think that A is 5 here, but really A is going to be 2. And that's because our function is natural log of x plus 3, and 2 plus 3 is 5. So, yeah, it's a little, I can get tripped up on these sometimes too. So, yeah, anyway, we've got 2 plus 3, so that's going to be 1/5. Okay. Now let's go over our derivative rules. We went over all the transcendentals that you got to know. You need to know your limit definition, but really just the first one as far as I'm concerned for now. Long term, we'll get some more practice with these second two. I just want to throw them out at you so you've been exposed to them at this point. That's not going to be on your test or even on your midterm. But long term, on your AP test, they might throw out some of these variations at you. So our derivative rules here, the first one that we learned was the power rule, and that's where we just subtract 1 from the exponent and multiply that by the, so we bring down the exponent, and then subtract 1 from the original exponent. So we have n times x to the n minus 1. And so if I want to find the derivative of h here, 5 times 4 is 20, so 20x to the 4th. Plus here you have 3 times e, which I can't really simplify because e is irrational, so I'm just going to leave it 3 times e times x to the whatever e minus 1 is. And again, e is irrational, so I'm just going to leave it in exact form there. Plus the derivative of 8x is just 8, and then the derivative of 2 is 0, so I'm done. The product rule is going to be the derivative of the first times the second plus the first times the derivative of the second. And so if I'm going to apply that here on function m, the derivative of x cubed is 3x squared, and then times the second is cosine 2x, plus the first, which is x cubed, times the derivative of the second. Now, the derivative of the second here is negative sine of 2x, and then using the chain rule, we're going to multiply by 2. So this is an expression that we probably could simplify, and you might consider just writing this second piece as like minus 2x cubed times the sine of 2x. You don't really have to. In fact, I'm kind of running out of room here, so I'm not going to do it that way. But just know that you could potentially simplify that little piece a little bit more. Okay, the quotient rule. Quotient rule is kind of similar to the product rule, not exactly, but it's got some similarities. We're going to take the derivative of the top times the bottom. So kind of the same start here with the quotient rule, but we're going to subtract the top minus the derivative of the bottom. And then finally divided by the bottom squared. So if I want g prime here, see if I can squeeze it in here. This is going to be a little tricky, but I'm going to try. We're going to start with the derivative of the top. That's just 3. Times the bottom, x squared minus 2, minus the top, which is 3x plus 5, times the derivative of the bottom, which is 2x, all over the bottom squared. And just because I'm out of room, I'm not going to go any further here, but you can hopefully see that there are some opportunities for simplifying, particularly in the numerator. After you do the distributive property, you have a couple of like terms you could combine, but I think I'll just leave it like that. All right, our last one here is the chain rule, and this is where we differentiate from the outside in. So we're going to start by differentiating f, so f prime, and then just leave the inside the way it is, times the derivative of the inside. So that is our chain rule. And so to apply it here, we've actually got 3 functions. It doesn't look like it, but we've got this x to the 4th, which is really our outside function. So with these trig functions that are not raised to the first power, sometimes it's helpful to rewrite it like this: sine of x squared, and then that whole thing to the 4th power. That's really what we're going to be differentiating. I mean, these two things are equivalent, but I think writing it like this will make it more obvious that your outside function is x to the 4th, or something to the 4th. You've got a middle function here with sine x, and then you've got an inside function here with the x squared. So we'll start with the outside function. Let's move all this out of the way. Okay, so the outside function is going to be, let's see, w prime is going to be 4 times sine cubed x squared. Okay, that's the outside function. I'll highlight that in yellow so you can see where that's coming from. Oop, that is not yellow. Let's see where that's coming from here. And then times the derivative of the middle, which was sine x. So the derivative of sine is cosine. So that's going to be cosine of x squared. Notice as at each step, I'm not changing what's inside of the parentheses. I just differentiate one thing at a time. So this is coming from the middle function. And then from that last inside function, we're going to have times the derivative of x squared, which is 2x. And this is another one that you probably could simplify a little bit further. I'm just going to leave it here just because I'm running out of room. But you could potentially like multiply the 2 times 4 to get 8x. And that's really the only thing you could potentially do. So that's it. This is going to be a quick video. I just want to go over all the derivatives that you need to know for this semester. There are less than a handful of other transcendental derivatives that we have not gone over that we will that we'll hit at the very end of the year. But I think this should be enough to kind of keep you busy, so to speak. Anyway, thanks for watching. You'll have a great day.